Huh.
You can have like a assignment sometimes, like a punishment assignment. It's just like a 10-page paper on the greatness of Mr. Gonzalez. The problem is you have to use sources.
That should have been one of the penalty assignments. All right, shut up, shut up. I have all the, if you didn't notice, I put an announcement up. I think you should all get an email, right? When I put an announcement up for the class. All right, so I have the 3 dates for the required tech talks. The assignments are up. The 2 dates for the required mini hackathons or shorter hackathons this time. So the assignments are either you got to take a picture of yourself there or do the penalty assignment. Love the hair. I've been trying to do the exact same thing, but the roots keep growing out. Just can't get it to stick. It's a problem. So they're going to be shorter mini hackathons. For all of them, you either have to take a picture of yourself at the event and submit that for full credit, or there's a penalty assignment. Now, the penalty assignment is not like an unreasonable assignment. So some of you might say, oh, I'd rather do this than go to the event. Don't do that. Only do the alternative assignment if you absolutely can't come to the events. These events are good events. Lots of internships come out of them. Lots of experience come from the hackathons. We're reliant on some of the upperclassmen at the hackathons to help you support developers and things like that. So do your younger classmates a solid by being there and sharing some of your wisdom from last several years of you learning to program and things like that at these hackathons. But if you absolutely cannot make them, there are alternative assignments up for those. I also put the Bible homework up, which is due by midnight on Friday of finals week. So make a note to do that sometime between now and then. Okay. That is a 600-page hand-drawn, handwritten scroll.
Someone's going to start that like at 11 p.m. Like 11 p.m.
It's your prerogative. Manage
Manage
your time. I should have made the assignment to actually write a scroll. I got that last semester. It's in my office.
I really think you should do that as an extra credit.
So I had a student last semester write the entire book of Mark by hand on parchment. And I have the scrolls in my office. It was some questionable academic dishonesty. It was an extra credit assignment. let's go with that ethically. So go ahead.
Oh, there you go. For required materials for the scores, you should have had parchment page.
you gotta have a calligraphy pen. Just we use Sharpies. I guess that was acceptable. There was a little bit of delay in the middle though, because there was some how we're having problems with shipping things and stuff like that. His second roll of parchment was delayed. It was great.
Speaking of which, I ordered a melon and I still get like that. It's now arrived. It's supposed to be
Well, everything's delayed these days. All right, so homework for today was to we were messing with child processes and just display to the screen like 0 to 9 or something like that, but in the correct order. I don't think I actually said you had to do it in the correct order, but I suggested that would be a good thing to do. All right, so let's go ahead and write this. And really, what are we examining with this? We're looking at how do variables carry over when a parent creates a child process. What do they have access to? What don't they have access to? And how does that actually work? We're going to explore that a little bit more today as well. All right. So let's dump all this. All right. So we're going to start with a counter. Start that off at 0. Now, the idea here is that we're going to spawn off 10 children, right? So we're going to spawn off 10 children and have each one do the next count. So the children are the ones who will actually print a 0 or a 1 or a 2, and the parent will increment. So I'm going to do something 10 times. All right, like that. We're going to do something 10 times. And what are we going to do? We're going to create a child. Then we'll ask the question, if I'm the child, so if my process ID is 0, then I'm supposed to print something out to the screen, right? So we'll say printf, the count is %d. And then maybe we'll do something like from %d. So we'll say count and we'll say get PID. So that'll show us that these are coming from unique processes. So we'll have the children say, here's the current count. This is who I am. Here's my process ID. All right. Now, if we are the parent, what's the parent's job? The parent's job is to increment our count. All right. But now after the child does their job, we don't want the child to loop back up in the for loop and starts creating more children. We want them to die. We want them to finish their job. So we're going to just go ahead and say return. All right, so that'll make, remember the return keyword makes a function immediately end. Go ahead. Yeah, the exit system call makes the program terminate. So yeah, you could accomplish it the same thing. But let's see, you asked the question, is it the same thing? The exit system call will ask the operating system to kill this process, whereas the return keyword makes this function immediately end. And if that happens to naturally come to a conclusion, then so be it. So in this case, they would have the same ultimate behavior, but they're not the same thing. That's probably the more accurate answer. All right, so if I'm the child, spit something out, then die. Okay, if I'm the parent, go ahead and increase count, spin back up, create another child, rinse, lather, repeat. All right, so we're going to do this without any sleeps at this point. Go ahead.
So why have a count at all?
Well, you could. So you want to just always print out I in here, which the child would have access to. The child would have access to the variable I. It would still work.
In this context right now, so I'm wondering if it was a future situation.
The future situation is what we're going to explore today, and that is kind of looking what variables are shared versus what variables are not. So having as a separate variable as opposed to our counting variable will work, but in this case it will be the same because they're two separate integers. They're both the same kind of animal. Maybe if we said, count plus equals 2 or something like that, then we say if we're going to count by 2s instead, then it's technically not the same. All right, so we're going to do, we're not going to have any sleeps right now. So we'll start with this. All right, and we actually saw that the parent died too quickly. So none of the children had an opportunity to do any of their stuff. So let's go ahead and, was it just sleep? And is it number of seconds like that? 1 second's plenty. All right, so that'll get the job done, but effectively we are still playing with fire here. That is to say that, and actually what I'll do here is I'm going to just put a sleep. I don't know, let's just say 4 right here. So I'm going to go ahead and have the parent create the 10 children all quickly and have each one of those children vie for CPU time through doing IO. And then I'm going to have the parent kind of chill for a little bit so that it doesn't kill off all the children prior to them being able to do stuff. And let's see what we get as the output. So now we see we get a more randomized output, right? All right, so this was kind of, I think Emily put it in. So you probably did something like this initially. Now, the thing is it's only important in this case if you actually care what order they're happening in. But what we're experiencing here is how the operating system is ultimately scheduling, right? So even though we know that this was the first child we created, and this was technically the second child we created, this child didn't get CPU time before this guy did, the 6th child we created. Make sense? So we're at the mercy of when does the CPU actually give that particular child process its CPU time. And we can't necessarily control the order. Having said that, if we go ahead and put a sleep in here, by putting in a 1 second delay, pretty good chance with only 10 children, they're going to get CPU time during that process. So we could probably run this over and over and over again and get the correct output just because we're delaying when we create the next child. But there is no guarantee of this. We're still at the mercy of the operating system scheduling. Go ahead.
So since we're doing off the function of the turn, technically we need the else or can this be like the job?
You wouldn't need the else. Yeah, since we are killing it off up here. Okay, so this kind of makes sense. That at some point we're playing with fire if you do care about the order that things get done, because we don't have control over the operating system scheduling. But we could, and I keep foreshadowing this idea of inter-process communication, when we actually start having these processes talk to each other, a child could say, I won't actually do my next output until the previous guy tells me he's done. We're not going to do that quite yet, but that's kind of where things are going. Since we don't have control over how the operating system ultimately works, we have to have some tools for processes to talk to each other to ensure things happen in the correct order. In this particular example, not the end of the world, right? But perhaps in another example, order of operation is really important. And maybe the child who was going to go second needs to make sure he goes second. And he can't just randomly be 5th because he's maybe reliant on other data. Does that make some sense? Okay. So questions about this. And in this case, we actually would not need, would we need? We wouldn't need to do a final sleep. Huh?
It might not take a lot of time.
Oh, I see what you're saying. I think it would. We still have an extra sleep. We're still sleeping for 1 more second on the last one. But again, it happens to be working because we feel like we're giving plenty of wiggle room to it. But if we start whittling this down, maybe we say 0.1. Yeah, you see the parent actually died off too quickly, kind of what you were saying. Let me just tell it to sleep for 4 seconds. That should get them all going. So we see that most of it was in order, but we get a little fumble down here. Go ahead. Yeah, right. So that's effectively interprocess communication. So a parent can wait for the child to actually complete before they create again. So and I think it's just wait, right? No parameters. Once an argument. Oh, here. Well, we'll look at this real quick. So I'm going to say, here's the. Just to show how this. I'm not sure if we need standard lib, but I brought it in regardless. Oh, we just pass it the null value. Otherwise, if you pass it null, it'll wait for probably the most recent child. If you don't pass it, otherwise you can pass it probably the process ID of the person you want to wait for, and that would be the child. So if you want to see that kind of in action, we would come down here, we would tell the parent to go ahead and wait for that particular child, the child they just created, to finish. So there's our 0 to 9 with no sleeps in there. Oh, it expects an int pointer. So this would be a form of, let's see, this would not be inter-process communication. This is still communication with the operating system. So rather than putting, although this is more precise. So I've been mentioning that, like with the sleep system call, we are basically just saying, hey, I'm going to put this thread to sleep for, or this process to sleep for a second, 2 seconds, half a second, whatever it is. And let's just hope that was long enough. Where in this case, we are specifically communicating with the operating system. The parent's gonna pause and tell the operating system, I'm going to wait until this process ID has completed. Okay. And at that point in time, the operating system would communicate back to the parent and say, okay, your wait is over. That process has finished. Okay. My guess is if you put null in here, that probably defaults to maybe the children we've created. I wonder what null ultimately tells it. Get the same behavior, but if we give it a nothing parameter, null's got to mean something. Let's see what it uses. That, see, this is what I was looking for in those man pages. Oh, see, it's actually what I passed. It was the wait status, not the wait PID. Yeah, so this is the version we're calling right now. If I want to wait for a specific process ID, I have to call this version. passing it the PID, passing it the status. So that would be this. Let's see if that'll run without the third parameter. Yeah, what's the third parameter? All right, so that specifically waited for that process ID. Let's find out what the status, what it wants for that status. So by default, it waits for us any sort of state change in a child of the calling process. So the default, if we just use normal wait, it will wait for a status change in the child of this process, which means if we spawned off multiple children, then it would wait for all of them, I believe. And it obtains information about what, so return a value. Just returns a value about the process ID. Oh, it only waits until one of its children terminates, the default one. So even if you spawn off multiple children, it'll continue going. As soon as one of them finishes. Let's see if W status is not null. So this would work in conjunction with the exit system call where a child could exit with a value and the parent could wait for that status. So that's that status change they could wait for. That would be an example of inter-process communication. All right. But in any case, so this would be sufficient and accurate for this. So would wait. Since we're only spawning a single child, and this code right here would guarantee it's always in the right order without us having to specifically just putting a timer in there to wait some period of time. Okay. So questions about any of that so far? We're getting the hang of how the fork system call works. All right, so now what we want to do is we're going to go ahead and tell the parent to wait for a second. And then at the end of that 1 second, the parent's going to go ahead and print out the current value of count. Okay. So if up here, I have the child change the value of count. Presumably within that 1 second we were waiting, it would have gotten its IO done and then also been able to increment count. So the question is what will the output of this program be? First time through, we're going to get a 0. That 0 becomes a 1. What's the output down here going to be? This count plus plus would have made it a 2, presumably. Then we sleep for a second. So does it matter which of these count pluses we get to first? If we add 1 to it, a 0 becomes a 1. If we add another 1 to it, a 1 becomes a 2. Any way you cut it, when we get to this line here or past this line here, it presumably would be a 2. Right? What will the output actually be here? And why? So we're going to see that the parent gets their original value, 1, then 2. So this is just the parent's increase, right? That child's increase, the count plus plus that came from the child, this guy right here had no impact on the version of count that the parent had. All right. What happens here is when the fork system call gets called, a new process is created, which is a duplicate of the original process. They have a copy of all the variables from the original process. But from that point forward, count, the child and the parent both have separate variables called count, that anything that they change to each other have no impact on each other. The child's version of count did just go up by 1, but that didn't have any impact on the parents. That makes sense? Okay, now let's make some guesses here. What if we did want to have an impact on the parents? What might we do? Anybody have some suggestions on some ways around this? Maybe doing something with pointers or something like that? Remind me, what's a pointer? Go ahead. Okay, so it's a variable built for holding a memory location, right? So if I came in here and I actually said this is going to be an int pointer called count. And maybe I say something like int temp is equal to 0. Int pointer count is equal to the address of temp. That's not address in this. This is address in that. So now count is a variable that holds a memory address. What memory address does it hold? It holds the memory address associated with a variable called temp. That's owned by the parent, right? So we create temp, local variable owned by the parent. We get the address of temp. Now, the children, all of them, are gonna have access to these guys. We go through 10 times, but now we're gonna say star count plus plus. Change the value that lives at the address of count by 1. Parent will do the same thing. Oh, I need to. It's printing out memory addresses. Give me a moment. Print out the value that lives there, not the we get the same result. So let's think about why we got the same result. Initially, there's one process. That one process knows about a local variable called temp. It also knows about a local variable called count, which knows how to hold a memory address. Okay. We go through, we're going to do something 10 times. We create a child. So after line 13 here, there are 2 processes. The parent and the child, both of which have access to both of these variables. Make sense? But should the value of count here be the same for both of them? So what I'm going to do is I'm going to go ahead and print out the memory address after the fork system call. So this is what the parent and the child think count holds. Parent and child both think count holds this memory address. Okay, so they seem to be in agreement with the memory address. So up to this point, count seemed to survive. It holds a memory address. Actually, let me do, well, we'll keep walking through it this way, then we're going to go the other direction. So what am I doing right here? When I say star count, that resolves the value of count. And then I'm adding 1 to it, changing the original value. Is that the same thing as saying that? Temp resolves to its value. We add 1 to it. Count plus plus, star count plus plus would be the same thing as saying temp plus plus. By comment. All right, so again, we see that both of them believe that they have the same memory address to that original value. And it didn't matter whether I incremented temp or incremented star count, because count holds the address of temp. Let's draw a picture here so you can see where we're going with this. Because this tells us a lot about how processes work in this version of Linux, which is different than an older version of Linux. We talked last time about how we could have crashed an OS by just calling fork a zillion times, right? So we're going to go ahead and draw a picture. All right, so we have temp, and we started temp off at 0. And we also have count, and we started count off at, I don't know, 0. Let's just do something like that. Simple memory address, okay? So this is the original parent. Okay, that's the original parent. We'll change this to, so now the parent gets a child, has a child process. Okay, we are seeing that both the parent and the child, and actually let me put a little text box next to this guy. This guy lives at memory address 0x123, for example, simplified memory address. All right, so temp is a variable that holds the value 0. It happens to live at this memory address. Count holds that memory address. Nothing special about the fact that parent knows about all that. But then we create a child process. Now, we've already seen, if we're just dealing with an int, that the child gets a copy of that int. And any changes we make to that copy are only temporary changes, or changes that happen only to the copy, right? So when we create that second guy here, this occurs. A second version of temp. Make sense? They're not both pointing back to the original version. They get their own copy. And we've seen that happen. We just saw a few minutes ago, they were both trying to increment count and they didn't have anything to do with each other. All right, because when we created the child got a copy of all those variables. So is it reasonable to think that this child will get a copy of all those variables. Yeah, that seems to be what's going on, right? You create a child process, it gets a copy of all the stuff. All right, but since count points to a place in memory where temp actually lives. So even though temp is this variable that's equal to a value, count we saw this is the value stored in count from both the parents and the child's perspective. They both hold the same pointer. Does that make sense? Let me just do this. We're just going to simplify our thing so we're not looping through a bunch of times. So we're going to say if the PID is equal to 0, if I'm the child, then I'm going to go ahead and I'm going to say star count plus plus. I will increment the value at that variable, at that location in memory. Oh, we're still doing it 10 times. Hold on. Give me a moment. If I'm the parent, I'm just going to go ahead and sleep for 4 seconds, to make sure I don't die off before the child has its chance to do its thing. So if I'm the child, I'm just going to increment count, print out the new value of count. And we see that count's current value is 1. No problem. Okay. So right off the bat, we see that both the parent and the child have a variable that hold that memory address. Okay. The identical memory address. The child went ahead and made a change at that memory address and then immediately printed out the value at that memory address. The parent waited 4 seconds. And let's go ahead and have the parent have the parent print out what it thinks is at that memory address. We can all agree that it took less than 4 seconds for the operating system to do some math. That guy got scheduled. All right. Well, we know we started off count at 0. Well, star count started off at 0. So we know if the parent's going to go to sleep for 4 seconds, this is all going to happen while the parent is sleeping. Count should go up by 1, presumably at the same memory address, right? Child then prints out the current value of count, saw right there. 3.8 seconds later, the parent will wake up and print out the current value of count. What do we expect the current value of count to be from the parent's perspective? Okay. Well, it's either 0 or a 1, right? If it's the same memory address and we change the value at that memory address, it wouldn't be unreasonable for us to expect this to be a 1, because I'm saying resolve the value at that memory address. So we're going to wait a couple seconds here. There's the parent's version of count. So what's going on? Go ahead. Ah, so tell me what you think that might look like, the virtual memory thing.
the physical memory address, the one that's being printed out right now, is the same thing. But when you create a file process, it is something physical.
Okay.
Somewhere else.
Yeah. So seemingly each of these processes is getting its own chunk of memory in which to operate. So even though both of these memory addresses were the same, somehow they are mapping to different places, right? How it's doing that mapping, we don't necessarily have to know. It could literally get a almost like the Java virtual machine where it gets its own copy of a memory space, or it could do, and this is the way it works for it's something we'll look at later, but the way memory works for the portion of memory protected by the operating system, protected memory, there is a mapping between real memory and system memory or protected memory. So you could almost think of this memory address being like a mask, and maybe it uses the process ID or something like that to fix the mask, or it just makes a copy of, maybe when a process is born. We kind of talked last time that maybe allowing a single process to kind of just take over the operating system isn't the smartest thing in the world. Okay, so maybe when a process is born, we kind of put it in a little bomb shelter, close the lid, and anything that happens in there, you're only hurting yourself, type thing. And well, I'll give you some memory. You have some access to some resources and things like that, but that's all in there. So seemingly something like that is happening. All right, so that's an important thing for us to recognize, because up to this point, when we think about memory addresses, we think about a single global pool of memory. And that's typically how memory does work. But now if we put ourselves in the shoes of a modern day operating system designer, we have to consider that, hey, we got to play protection to some level to make sure that our memory, the programs don't run amok in memory. All right. So we saw that happen at the software level with the advent of like a language like Java, which took away your ability to manipulate memory. But now we're using a language from the early days of operating system C, which, hey, all day long you can manipulate memory. You could just add values to memory if you want. So I can increment memory and it'll jump by 4 bytes in this case, because that's how big an int is. So count plus plus would be 4 bytes bigger. You can do pointer math. Presumably that would then be a new place in memory, but it's actually a new place in different memory. So it's a process seemingly gets its own copy of everything, including memory space somehow. Make some sense? Go ahead. Okay, so you want to have the child go to sleep for a little bit, and here we can reduce that a skosh. So what you're asking is, did this memory actually still exist, but the child actually died off before the parent took over and it kind of reverted back? All right. So in this case, what we're going to do is we're going to increment the value at that memory location. We'll immediately print the value, fully expecting we're going to get a 1 instead of a 0. But then this child will not die. It's going to go to sleep for 20 seconds while the parent has time to wake up and print out what it thinks is at that memory location. Still a 0. Okay, but it's a good question. She was asking, did the behavior change because the child died? When the child died, that went away. This stuff's still preserved. Go ahead. To use what? Threads are going to suffer from the same thing. Yeah. Yeah. Same problem. So how do we do it? Let's say I really want them to share that variable for no good reason, right? You know, this isn't like we're not landing on the moon here, but you know, we just really want them to keep that variable in sync. It's important to us. What can we do? What are some possible solutions? Is it a reasonable thing to ask that we have two separate processes that might want to share some information like this variable? We're coming up with a stupid little example of just sharing an int because that keeps it simple, but it's not unreasonable to say, hey, these guys should probably be able to work with the same values and have an impact on them. Go ahead. I'm sure it does, but none that are going to allow you to do this. Well, actually, it takes no parameters. So actually, no, it takes nothing. There isn't multiple versions of it. Yeah. Okay. So maybe, or there's something else built in the operating system that might solve this problem. Okay. And that's where I kept referring to IPC, interprocess communication. We have special tools for allowing us to do that. But now if we roll back and put ourselves in the shoes of an early day programmer that maybe doesn't know a whole lot about the operating system calls, or we go far enough back that some of these system calls weren't there. Operating system number one, okay, whatever the first OS was that anybody wrote. What probably existed in the very first operating system? We go back earlier in our slide, somewhere we asked, what are the things that an operating system does? So here, what services does an OS provide? So in the very first operating system, did it probably provide IO? Ability to read something in, ability to write something out to the screen. Yeah, it's kind of it's not really a computer if it's not doing that, right? Did the very first operating system support drivers? Probably not. That stuff was probably hard coded in. And when I say stuff, I mean the completely generic hardware that whatever the bare bones minimum hardware was, which was probably monitor and keyboard. How to talk to a VGA compatible monitor. And actually back then, it probably wasn't even a standard VGA thing. It was probably just how to talk to monitor and keyboard. Okay, this is before mice existed. All right, did it have some level of process management? We can't really imagine an operating system. I mean, it's not a computer if we're not running programs on it, right? That's kind of the purpose. You're telling a computer what to do, and that comes in the form of a program, and programs exist in the form of a process or something similar, whether they called it a process in the very early days or it was something very much like that. Okay. Presumably, based on this conversation here, let's just say no direct interprocess communication existed. They didn't have special little secret communication devices. They weren't handing out walkie-talkies for the processes or process-like things to talk to each other. All right, that maybe wasn't in operating system number one. All right, did we have processor management? Early computers probably all had a processor. Not very fast, probably compared to today's stuff, but we had to manage it somehow. And you know, we talked earlier about you know, first week of class about some of how operating systems have kind of evolved, and our very earliest computers ran one program at a time, right? So presumably the processor management was fairly simple. Run program till it's done, right? We weren't doing context switching where the thing was leaving the thing, coming back. It was just like, look, you have the floor, go, okay? What about file system? Did the idea of a file probably exists day one of the computer? Go ahead.
And might existed, but it was very low level.
How is it a computer? Okay, so rewording that a little bit. So something like a file existed, similar to, like we said, something like a process existed, whether they called it a file or they just called it called it data, whatever. Typically, a computer is operating on something, and that something has to live somewhere, right? Okay. Whether it's living directly in system memory, or you go back to the earliest computers, they had some sort of magnetic media. Some of it was removable, some of it maybe was built in. There was probably a hard drive, so that when you turned the computer off and then you turned it back on the next day, the stuff persisted. If it didn't do that, then it's, I guess it's a calculator at that point, right? Without memory, just, you know, shut it down, you come back the next day and you just start over. All right, so the idea of a file likely existed in the very first operating system, or really early on, right? Because now we're kind of talking about, well, at what point was the first thing? At what point did it actually become called an operating system versus some sort of weird Frankenstein type thing that was, you know, slowly evolving into what we look at today? So file system probably existed. And we're going to say, yes, it existed for the sake of this conversation. Now, our modern day operating systems have a lot of security built into them. At some point, well, at the very least, you go back farther, less and less and less and less security, and probably the very earliest computers, they didn't even think about that. They weren't hooked into a network or anything like that. It was just, you just needed to lock the door to keep people from going in and getting files from your computer or something like that, right? So probably the OSs didn't have a whole lot of security stuff built into them. Yeah. Maybe. I think it's fair to say that probably was present relatively early in computing. Like, hey, we might want to have more than one person using the same computer. But really, in the earlier days, that was handled through your floppy disk, you know, or whatever, you know, removable media. You know, when it was your turn to use the computer, you showed up with your disk, you put it in there, and now you got your stuff. This is you, right? You would even boot DOS off that. So the earliest computers didn't even have a hard drive. You only had the external media that was in various, you know, the floppy disks, the 5 1/4 inch floppy disk, which was actually smaller than the original. There was disks that were, I don't know, maybe 12 inch. I don't remember what size, but the first discs that the consumer computer user used was the 5 1/4 inch floppy disk, and it was floppy, right? There's Dr. Lockley. I have one of those over there somewhere. It's got a real chance if it's in that cabinet somewhere. Okay, not the 5 1/4 inch ones that were floppy-ish, but floppy ones. All right, so maybe some form of security, but probably not. All right, so we can rely on the idea of files being there very early on. What's a file? Go ahead.
It's a document and be in form of a text file with
Okay. Document that holds data. Okay. Document that holds data, or data could be whatever we're able to write to a file, right? So document, maybe we call this a named document that holds data. what is a file system? We talked about some examples of file systems. We talked about FAT32 and NTFS and those things. Go ahead. Okay, manages files. And typically when we're thinking about a file system, we think about two things, right? Files and directories. So we kind of think of this hierarchy, an organizational tool for working with files. But at the end of the day, so we call this guy an organizational tool for managing files. So at the end of the day, we at least have a file. You know, maybe the very first operating system didn't provide a very robust file system. You know, maybe it's like, look, you want data? Maybe it was not even a file, it was the file. you had the file, and it had to be named something very specific. You know, file.dat or something like that. Okay, but we had a file. So a file is a named document that we could put crap in. All right, so let's go and we'll go in here. Now let's keep using this guy. So let's say info.dat. Into.dat info. Now, what I put in this extension is meaningless, right? It's for kind of human eyes only. You know, you've seen things like .txt, you've seen things like .exe. Typically in modern day computers, this would be called a MIME type. You look at the extension, that should give you some information about what kind of crap is in that file. But at the end of the day, a file is a file. If it happens to be an exe, it's probably a binary file that's executable. So you might decide, okay, well, because they've named it .exe, I'll go ahead and run it through my program runner ability that the operating system has. But you might just have a poem written in that file and just happen to name it .exe. All right, so what you put in an extension here isn't all that important, but I'll call it info.dat since we're kind of living in the olden days of operating systems where typically an extension might be the .dat for data extension. Okay, info.dat. All right, and we're going to put maybe a couple of words in there, some stuff. All right, now what we want to do is we want to get this information into our program. So if we want to read from a text file, we're going to need standard lib, because I think that's where the file thing is. All right, and we're going to go ahead and we want to give ourselves, this is for the number of line, but we want to have a pointer to our file. So the type is going to be a file pointer. All right, so that's going to be a value that's going to hold a pointer to that file using some sort of system call that knows how to connect this running process to our file system. And we're going to use fopen. So we're going to say, actually, I'm just going to go ahead and give it the value right here. So fopen, and fopen takes in the name of the file. It'll take in the full path of the file, but we have it living in the same directory. So we're just going to put the file name. So the name of my file was info.dat. And we're going to open it up for reading only. Presumably, very shortly, we're going to want to also write to it. Now, this is doing some error checking that you see here. So when it gives the value to the file pointer, if it gives you something that's, if the return value of that is null, that means, hey, there was a problem opening the file, yada, yada, yada. We don't error check in my classes. So we're just going to say, hey, this is mostly for the reason we don't want to just have a whole bunch of garbage. We want to focus on the actual thing. So if you were writing this for a real project, probably error check and make sure that the file you tried to open was legitimate. We're just going to let our programs crash gracefully in the event that we try to open something that didn't work. All right. So that's why I'm not wrapping this thing in an if statement where we might say, hey, we had an error opening a file, whatever. All right. So now we want to be able to read something in from that file. All right. So we have this thing called fscanf. Now notice here that we have this variable called num here. And this is going to give us an idea, kind of talking through this, is going to give us an idea of how a lot of Linux system calls work. So I'll go ahead and just give myself that variable num. We don't really know what that's for yet, but we will. All right. So now what I'm going to do is I want to read into, well, fscanf will read something from a file. So actually in this example here, I'm just going to put a number in there just to make it compatible with this example. All right, so I want to read something in from a file. Now, there exists a thing for reading in from the user called scanf. Scanf allows me to read something in from the keyboard, and it's called scanf. And fscanf reads something in from the file. So they're very similar type things. So I'm going to say fscanf, here's my source, the file pointer. This is what I'm reading in, a decimal value. And then we're going to pass it a pointer to num. So fscanf, I'm going to pass it my file pointer. I'm going to pass it the kind of value that I'm reading in. And then I'm going to pass it the address. Oh, that's the wrong language. The address of num. Oh. So there's the value that we read in from the file. I change the contents of my file to be a 6. Run this again. Now it'll read in a 6. All right, that makes some sense. So this guy drove what I was reading in. This %D. I'm reading in a number. Where am I reading it? I'm reading it into this address. So scanf says, where am I reading from? The pointer to the file. What am I reading? Where am I going to put it? So if I say char pointer, let's do it this way. Oh, well, that's okay. I don't want to have to explain that this exact second. We'll explain it soon. Go ahead. Oh, just stretching. So instead of reading in a number, I can say I want to read in a string. Now, what I'm doing here is a string in Old C is a character array. So I'm going to go ahead and I just built an array that's capable of holding 1024. All right, so buffer is a character array. Now, actually, I can give it, I think that'll maybe make it go away for a second. Yeah, there we go. No, no, still like it. It's fine. So buffer is a memory address, but it was just created using the syntactic sugar of creating an array. So this asks for 1024 bytes because that's how big a char is in C. This gives me 1024 bytes, and we read that guy in. So I pass, I'm going to read something in from my file. What am I reading in? I'm reading in a string, and this is where I want you to read it. Actually, maybe we do that. Yeah. So this guy's already going to be a memory address. So I don't pass it the address of buffer. I pass it buffer itself because this guy's going to be a memory address. Just like any other array in any other language. An array boils down to the base address of the array. And remember, arrays are fast because we can calculate where we are in the array from what bucket we're in. Right, so this is going to be the memory address. I'm reading in from the file. This is what I'm going to read in. This is where I'm going to read it. And then we'll just go ahead and output it. Okay. So now we've read something into our file. The next thing we'd want to do is write something out to our file, right? And we'll look at this. We'll probably write it next time. So I can open up my file for writing. Again, error checking. I can read something in from the user. So here's that example of using scanf to read something in from the user. So I'm going to ask the user to enter a number. User types it in. I'm going to read in a decimal value into the value num. So we're seeing how these functions typically are working. I give it the address where I want it to put the answer. Rather than it returning the answer to me, we commonly pass it the address of where we want it to put the answer. So it actually ends up being, the result ends up being one of the parameters. All right. And then I went ahead and I'm going to do an printf. Just like we've seen printf for writing crap to the screen, we're going to say printf for writing stuff to a file. And we're going to write this this number. Right, make some sense? What do I want that to? So let me actually give you those two examples. Oh, actually, we'll just do it with the original file. So we're going to open that file for reading and writing. Start this guy off at a 0. We'll read it in. We'll increment it. So we'll print out, we proved what we read in first. Then we'll increment it. Then we're going to do printf. And we're reading in a decimal here. And what are we going to print? We're going to print a decimal value. From num. Actually, it's not the address, it's the actual value. So open up the file for read write, read in the current value, prove what it is, increment it, write it back to the file. It still has a 0 there. I need to do a close. Where's my, oh, it's F close. Allow me to write to my own file. Bring it open. I know we're out of time. So I want to make sure I give you something to work with. So it's read, it's reading and writing. It's W plus. All right. So I'll patch this up a little bit, but this showed that we wrote it. Where we read it in, it was 219.18 that we read in because I read it in wrong. But then we incremented it, we wrote it back out. So what I'm going to have you do is I'm going to have you for your assignment count with a file using the children. Okay, using some of the same techniques we looked at today with sleep. So I'll make sure I give you something that reads in a number, writes that number back out as a starting point. Questions, comments, concerns, bribes? Okay, I'll see everybody on Thursday.